Hello and welcome. This is our 2020 Virtual Community Summit for the HPCC Systems Open Source Community. This is a different event, as you noticed. We have changed our format from physical to virtual. There are, of course, reasons why we need to move this way. But besides those reasons, this is going to really help us open this community day to a very large number of people in our community. Right now, we have hundreds of people from external places and thousands of people from LexisNexis resolutions joining us for this day. So I hope that this will be as a great an event as it was in the past years, and even more because we can have more participation and we can have a wider spread of the HPCC Systems open source community. Today, we will have a day structured across plenary sessions, like the one that you are watching right now from your computers, and breakout sessions. We will have plenary sessions right now covering 2 other speakers, and then there will be 3 breakout tracks that will then join us back into the plenary session towards the end of the day. We will have all of those sessions recorded. Breakout sessions have 4 sessions simultaneously. So, of course, you can only watch and listen to one. Maybe if you are a great multitasker, you can listen to 2 of them. But if you want to go back, because this content is going to be very good, you can always go and rewatch some of the other ones that you couldn't attend. So do not miss that opportunity. Stay tuned for those links and go back and watch the ones that you missed, and perhaps rewatch the ones that you watched. Now, there will be across the day 4 main tracks. Those tracks will be data lake, and as you can see, data lake is part of the main theme for our day. Cloud is also part of our main theme, our building HPCC for the public cloud. And I won't say more about that because Richard, who will follow me, will say quite a bit about it. And then we will have machine learning, of course. We couldn't miss machine learning, which is so top of mind for a large number of people in this community. And platform extensions. And this is to make the platform better and faster and more powerful and integrate better with our systems. We will have also posters and poster presentations. If you go through the main portal, and I hope you've been spending some time to explore it, you will see that there are 4 posters that you can watch. Each one of these posters has a video. You can look at the posters, and you should be voting for the posters that you like the most. We will be giving awards to the posters, and we want you to interact with those presenters. A lot of work has been going in there. If you have been browsing them, there are excellent posters. As a matter of fact, it's very hard to say which one is not that good. They are all very good. And we want you to interact with the presenters, and we want you to participate with those people. Some of them are students, some others are professionals. Just go and look at them. And we have also, as part of the format this year, similar to what we had last year and the year before, an interactive expo, but this is all online. So if you go to your main portal, you can click on Interactive Expo, and you can see the expo booth, participate there, also interact with the presenters, and learn more about some of these great demos that they will have there live for you. Now, throughout the entire day, please interact and participate, ask questions, try to make this your day. This is for you, and you are the most important person in this entire event. So please be active, participate, engage, help us be better, and contribute any way you can to our community. Last but not least, we have also changed the general format of awards. In the past, we used to use physical awards in some cases because, well, we had a physical room and we had people there. Nowadays, it's slightly harder to do that. So we have opened a new program with digital badges. These digital badges allow you to receive your badge, your award, your recognition, and show it and display it in your social media sites and make others know that you deserved this distinction. So please look at the digital badges that we will be providing and make them, for those that you get, make them yours and make them part of your social media sites and your profiles. I think it's important because the world is moving digital, and having this type of digital recognitions can help also spread the word about HPCC. Now, without any more preamble, I want to open now this plenary session to Richard Chapman. Yes, the one, the only Richard Chapman. He will be talking about our journey to the cloud on the HPC Systems Community. Richard, the floor is yours.
Thank you, Flavio, for that introduction. And hello, good morning, good afternoon, good evening, or whatever it happens to be, wherever you are, and welcome. I'm going to talk today about cloud computing, and let me just see if I can get the first slide up. There you go. Cloud computing and how the HPCC platform is changing to take advantage of it. I'll talk a bit about why we're interested in cloud computing, a bit about how HPCC has supported it in the past, but mostly about the major changes we've made in the platform over the course of 2020 in order to make HPCC cloud native and exactly what that means. I will also try to explain some of the reasoning behind those changes, what additional changes you can expect in the next year or two, and what the implications of those changes are to the way that you use HPCC. Finally, I'll talk a little bit about what the implications are for the future of HPCC if you don't want to use a cloud environment. I'm not going to dwell for long on the advantages of cloud computing. There's lots of material out there on the topic, but I'll just mention a few that are particularly relevant to HPCC and how and why we are making the changes that we are. The biggest advantage, I think, is the agility that a cloud-based infrastructure can give you. Provisioning hardware in a traditional data center can take weeks or months, depending on how streamlined your processes and your bureaucracy are, where provisioning a new cloud system can be done in a matter of minutes. This ability to change rapidly leads to other advantages. For example, if you can easily change your system, you can also easily experiment with new configurations, test out new versions, and so on. So there's an opportunity for a big gain in innovation. If you can provision your computing capability just in time, there's also an opportunity for cost savings by not paying for hardware until you need it. Cloud systems, if used properly, can also make it much easier to support redundancy and disaster recovery. And finally, cloud computing is trendy. That's not a completely flippant point. Using modern technology and techniques can impact how easy it is to attract and retain technical employees. But it's not all upside. There are some concerns too. Security is a big one. Is your data safe from other users of the same cloud or from employees of the cloud vendor? But so too are performance and cost. The more awake among you will notice I've listed cost on both the advantages and concerns lists. While cloud computing has the potential to reduce costs if implemented well, it also has the potential to increase costs if done badly. So careful monitoring, planning, and control of costs are important. HPCC has been cluster-based ever since its inception in 1999. Use of a large number of compute nodes working in concert is at the heart of the design and the name. So the cloud should feel like a natural home for HPCC. And indeed, HPCC instances have been successfully run on the cloud by a number of customers and internally within LN for a few years. But these have always been lift and shift type operations, taking the existing HPCC setup and dropping it onto a set of cloud-based virtual machines, which meant we were unable to easily take advantage of some of the benefits of cloud computing, such as simple scaling up according to demand or scaling down so that you are not paying for resources when you're not using them. Back in 1999, storage was expensive. A 1 terabyte EMC rack cost about $1 million by the time you'd paid for the data center infrastructure you needed to support it, and it took up a lot of floor space. So when we noticed that our rack of compute nodes, each with its own hard disk, could give us a significant amount of distributed, redundant, fast storage for free, it was only natural that Thor and later Roxy would take full advantage of it. But nowadays, when terabyte drives come free in boxes of cornflakes and are not much larger than a postage stamp, some assumptions need to be challenged. Of course, storage needs have also grown, and a terabyte is not considered big data anymore. Using the local storage on Thor compute nodes just because it's there is not such a no-brainer as it was. And in fact, we've been gradually moving away from that assumption in our on-premises installations too in recent years, with data stored on one Thor for use by many others or shared between multiple Roxy clusters. In January 2020, in those dim, distant days before anyone had heard of COVID-19 and we were still able to hold face-to-face meetings, my team held an off-site meeting in Windermere in the beautiful English Lake District to set about designing the next generation of the HPCC platform that would be truly cloud native. Fortunately, the weather was appalling all week, so we were not distracted by the wonderful scenery around us and were able to focus on the task at hand. By the time we left, we did so with a vision of a new version of HPCC that would take full advantage of all the benefits that a cloud infrastructure could provide, without losing any of the benefits of the HPCC ecosystem that have been so effective for the past 2 decades. We would use a containerized architecture, zero touch, with one HPCC process per container, which starts when the container starts, stops when it stops, and keeps no internal state. We would maintain cloud neutrality by treating Kubernetes as our target platform. We would change how the HPCC platform configuration is managed to use industry standard tools and paradigms. We would support off-node storage for Thor and Roxy data, as well as for generated DLLs and other persistent state. We would support direct, seamless access to cheaper cloud storage systems like S3 or Azure Blobs. We would remove all requirements for HPCC to know cluster topology in advance by using named services, discovery, or other techniques as appropriate. And we would support on-demand scaling, both within a component, such as adding more agent nodes to a Roxy as needed, or of entire components, such as starting as many Thors as required to execute submitted jobs, or even executing multiple portions of a Thor job at once. I'll go into a bit more detail about each of the above in the following slides. One of the design patterns for modern DevOps style deployment, especially on cloud systems, is the concept of zero-touch deployments. I was looking for a definition of this term that I could put here, and I found it's been a little overused, but actually at least 2 of the common usages are applicable. The way I interpret it is as follows. Once your servers are started and your application is running, you should not touch it. Reconfiguring is done not by making changes to an existing server, but by deploying a new application on a new server and tearing down the old one. A related meaning is that you need to be able to bring up your system using automation tools without requiring any intervention. In a cloud environment, where the server you get today may not be the one you get tomorrow, you can't afford to have any state stored on the server, whether in local files on the server's disk or information controlling how the server is configured. A good analogy I've heard here is that you need to treat your servers less like pets and more like cattle. So you don't manage a server and nurture and maintain it and configure it throughout its lifespan. You just have a herd of them that you treat as interchangeable. One thing that was very important to us when designing how to make HPCC cloud native was that we didn't want to be tied to one particular cloud vendor. As an open source project, we cannot predict all the different scenarios that the HPCC may be used in. and there are many reasons why HPCC users might want to pick one vendor over another. Fortunately, all the major cloud vendors provide full support for using Kubernetes to manage a set of virtual machines allocated from their clouds. And by treating Kubernetes as our target platform, we can target all cloud vendors at once. Having said that, there are unique features of each cloud vendor too that we don't want to treat as out of bounds. For example, Azure Blobs or Amazon S3 storage. So we are providing plugins that integrate access to such features as appropriate. The standard way to configure a Kubernetes cluster is to use Helm. This provides for a greatly simplified way to specify the configuration of the HPCC system without needing a specialized configuration tool to edit it. We now use simple YAML files to specify the configuration. Kubernetes takes care of starting and stopping containers as needed to match both the requirements specified in the Helm chart and any dynamic changes to it to handle fluctuating load or temporary jobs. If you're going to keep your servers alive only for the duration of a single work unit, then you can't rely on data stored to their local disks to be available for the next job. In fact, you can guarantee that it won't be. So the implications of this, for Thor at least, is that we need to store our data somewhere else. Cloud vendors like Microsoft Azure, Amazon AWS, or Google's GCP offer a variety of storage options with different pricing structures, performance characteristics, and access methods. One thing to note is that many of these storage options charge not just by how much data is stored and for how long, but also charge per access and or per megabyte accessed. So we need to be a little bit cautious about unnecessary accesses. For example, preemptively reading data that you think you're going to use later, but in fact don't, may end up costing you money. Ephemeral data, such as spill files, produced as part of Thor execution, can be stored on local disk. One of the most exciting opportunities in a cloud installation is the potential to reconfigure dynamically in response to load, so that additional resources can be made available at times of higher demand and released again so that you don't have to pay for them when the load subsides. There's two ways in which auto-scaling impacts HPCC cloud systems. Firstly, any components that operate on a single work unit at a time, ECLCC, HTHOR, and Thor, for example, do not need to consume any resources when no work unit is running, and conversely can run as many instances as there are work units waiting. This is done by launching a Kubernetes job for each work unit that needs to be processed. Secondly, components that deal with short-lived transactions, Roxy or ECL Watch are the classic examples here, can add or remove servers quickly and automatically according to load. One implication of this is that the topology of the HPCC system is no longer fixed at the time the cluster is started. This means we needed to find and remove any code that assumed that it was. So what do all these changes mean for the HPCC platform developers? For those that manage HPCC installations? Or for the ECL programmers that use them? Probably the change that will have the biggest impact and the biggest challenge for making sure that everything works is the change to move the data off the compute nodes and store it instead on separate storage systems. These may be persistent volume mounts, blob storage, or some mixture. For anyone unfamiliar with Kubernetes terminology, persistent volume refers to a file system mounted by the containers in your system, but whose lifespan is longer than the containers themselves, and which is most commonly physically located off the node that is running the container. The code running on the container can access the files on a persistent volume using standard POSIX calls, but the bandwidth available will not be the same as when accessing local disk. Another big change is that everything is now managed at the container, or more accurately, from the Kubernetes point of view, the pod level. Where previously HPCC components were executed as processes and managed via daemons or init scripts to restart automatically should they terminate, now everything is managed as a container, which runs the relevant HPCC processes when it starts up and terminates when that HPCC process finishes. Kubernetes takes care of making sure there is the appropriate number of these containers running for each HPCC component at any time. Because Kubernetes will provision and deprovision these pods as needed, and because there is no persistent state or data stored on the pod's local storage, there is now no need to keep processes running or being paid for when they have no work to do. In the HPCC cloud system, a Thor cluster will be created on demand when a work unit is submitted, rather than being left idling waiting for jobs, as is the case in the traditional bare metal systems. For this to work, we needed to speed up the Thor initialization process, and even so, there's a bit of overhead that may mean your Thor job takes a little longer to get going compared to submitting to an idle Thor on our current systems. But, and this is a huge difference, if the Thor is not idle, on the traditional system today, you may need to wait minutes, hours, or even days for the current job to finish, where on the cloud, we can just spin up another Thor. It's not just Thor that we've applied this on-demand spin-up to. We can also run each ECLCC compilation or each HTHOR work unit as its own Kubernetes job on a freshly provisioned Kubernetes pod. This allows the system to automatically scale up when needed without paying for processing power that is sitting idle. It also allows for better isolation of work units from each other. Because pods are launched on demand, we do not have a static environment, and editing the environment using our old config-env tool would simply not work. In addition, because our target is much more standardized, we don't need quite so many options, so we're able to simplify the configuration using Helm. In the next couple of slides, I've tried to highlight the key differences that users will see from the point of view of two different classes of user. In a moment, I'll talk about the key differences from the ECL programmer's point of view, but first, a few things that anyone designing or maintaining an HPCC cluster from the operations side of things may find interesting. The biggest change comes at the point of provisioning your machines. Basically, you just leave that to Kubernetes. No more buying nodes, racking them up, installing operating systems, installing patches, etc. Bringing up a new system should have a much shorter lead time, and conversely, deprovisioning a system that is no longer required is trivially simple. Secondly, as already mentioned, the configuration process using Helm is much simpler. Using Helm for configuration in this way is also more industry standard and plays nicely with tools like Terraform for integration into a configuration as code workflow, or with tools like kubescure for spotting configuration errors or poor practice. Finally, for anyone trying to design or size a system using HPCC on the cloud, you should be aware that the equations will be different in terms of what the running costs of a system of given size are, as well as in terms of what the performance of a given size system are. A cloud-based 400-way Thor is not equivalent to a bare metal on-premises one. Will it be faster, slower, more available, less available? What about storage? Traditionally, storage was part of the Thor, but now you decide and pay for your storage independently. The fact that the storage is decoupled and the processing and storage can scale much more flexibly may also change the way that you want to provide HPCC clusters. In particular, where traditionally a Thor or a Roxy cluster was something big, expensive, and time-consuming to create, once you've created one, you'd tend to want to use it for as many things as you could. But if they're simple and cheap to create as needed, it may well make sense to have rather more smaller, more single-purpose ones. For ECL programmers, the changes should be a bit less dramatic. The ECL language has not changed, and all your existing code should work as it did before. The fact that Thor jobs need not be blocked behind others may change the work patterns a bit, though. One thing we need to be careful of as we move to the cloud is that without the fixed capacity of the traditional system, there is no automatic break limiting the number of compute hours that can be used per day. Will this lead to uncontrollable costs as ECL programmers submit more jobs? We do have plans to report the costs of a job in real dollars as charged by the cloud provider, in each work unit, as well as to allow a job to be killed if it reaches a specified cost limit. It's also possible to limit the number of simultaneous Thor jobs that are allowed. What if I don't want to move to the cloud? Perhaps the security concerns are just too much, or I have customers that will not allow their data to be processed outside of my data center. Will I still be able to use HPCC? In HPCC version 8, there is still full support for the traditional HPCC installations and configuration that you're used to. Internally, the code base is probably 98% the same whether you're using the cloud native or the traditional bare metal versions of the platform. But will we want to support these two variants forever? Probably not, especially as the cloud native systems installation and configuration system is significantly simpler for us to support than the bare metal version. But that doesn't mean we'll be pushing everyone out of the data center and onto the cloud. A containerized system makes a lot of sense inside the data center too, and Kubernetes can be run using fixed bare metal servers as well. So eventually, I expect there will be a single version of HPCC supported, but it will work just as well on premises as it does on cloud. So that's the plan. How far have we got? As mentioned previously, the design and initial timeline were completed back in January. In April, release 7.8 had the first experimental Kubernetes support, including the ability to bring up a containerized system with all HPCC components, but without persistent storage. In July, release 7.10 added support for persistent data via persistent volume claims, and version 7.12, fresh off the press last week, has more complete support, including configurable storage via Azure or S3 blobs, ingress-egress control, resource limits, and more. At this point, the design is fairly well settled, though there are still things that need to be completed, and the system is not ready for production use on the cloud. The plan is to finish all of those loose ends before the 8.0 release scheduled for early 2021. Some things we don't know yet, and we do need to know these soon. Just how big is the impact on typical Thor jobs of having to read the data from off-node storage? What forms of off-node storage will work well and which poorly? How much will we have to pay to get what level of performance, both in terms of compute costs and data costs? What about reliability? How often will cloud nodes fail unexpectedly or be brought down for maintenance when we would prefer that they weren't? What will that do to our availability? With storage off-node and nodes automatically restarted, availability may even be improved. What about Roxy storage? Will any form of off-node storage be fast enough for Roxy, which spends its life doing random access disk reads? Or will we need to run Roxy on nodes with fast attached storage and copy the data onto those nodes at startup? If so, what will that do to Roxy startup times? What about logging? If your logs are stored on local disk, they'll disappear when the container terminates. Sometimes that's what you want, but it can make post-mortem analysis difficult. Elk is almost certainly the answer here. So there you have it. HPCC is going cloud native, and I hope that you are excited about that prospect as I am. There's been a few blogs produced by the development team describing some of the changes in the cloud native version and how to use it. See the specified link. If you want to know more about Kubernetes, just Google it. We're going to hold questions until after Roger's session, but do please ask them in the chat, and Flavio is collating them and will pose them all to me at the end if there's time. So with that, I will hand you back to Flavio, and thank you.
Thank you very much, Richard. That was a brilliant presentation. I loved it. And I already have questions of my own, plus a couple of questions from the audience. So we'll hold those for the end. Now, I don't want to spend much time at this interval, so let's get Roger Roger is going to talk to us about data lakes, and this is an introductory presentation that will get us into the Data Lake Summit track throughout the rest of the breakouts and part of the theme of the day. So, Roger, without any more preamble, the floor is yours.
Hello, everyone, and thank you for attending our community day. In Richard's presentation, he mentioned the design meeting held at Windermere, UK. I had the privilege of participating in that meeting. When I heard Richard say that it was in January 2020, I did a double take. I thought he had misspoken. It had to have been January 2019. But I soon realized that he was right. That's a huge amount of progress that the team made in less than a year. But I think you'll all agree they did have a certain advantage. 2020 has been a very, very long year. When the team came up with the vision for HPCC systems in the cloud, I was immediately struck with the elegance and the after-the-fact obviousness of the design. By the way, when you struggle to find the right design and you, after the fact, say, why didn't we know that in the beginning? It's obvious. It usually means that you have a very, very good design. That makes HPCC clusters more economical, easier to deploy and administer, and a perfect fit for a wide variety of organizations. Immediately after that, I was struck by a second realization. While longtime HPCC users know the value and power of our solution, the job of explaining it to new users and prospective users just got significantly harder. You might ask, where's the cluster? I don't see a cluster. Isn't the cloud my cluster? Big data. I have an unlimited data storage and processing power in the cloud. Why do I need HPCC when the cloud gives me all the power I need? What's it really for? Well, fortunately, we've been recently reframing the way that we talk about our system in a way that makes as much sense in the cloud as for on-premise hardware. It also happens to capture the essential strength and value of our solution, an enterprise data lake management system. I'll explain what we mean by enterprise data lake, why it's economically important, and why HPCC is the best-in-class solution for building and operating enterprise data lakes. Let's start by taking a look at what we mean by a data lake. A data lake is an architecture and methodology for managing complex data. Data lakes are used today by many successful businesses that make their living as providers of data. More and more enterprises are adopting data lake technology to manage their internal data so that it can be effectively leveraged for all aspects of their business, as well as their relationships with customers, suppliers, and competitors. Data lakes are designed to handle complex data that may come from many different sources and have many potential uses. It does not replace relational database systems or object database systems for managing structured processes like accounting and payroll. But it's optimized for the generation of value from the data produced by these types of systems and many other sources of data. Realizing the value from any set of data is not a one-time thing. Value snowballs as data is refined, integrated, and analyzed. It's an incremental and continuous process. Some people think of data lakes as a playground for exploring data and looking for nuggets of value. Then those discoveries are transferred to another team to productize using a different system and architecture. In our view, that's a big mistake. Not only does it greatly delay the path from discovery to realization of value, but it hampers the discovery process itself, which must build upon the solid foundations of previously stabilized knowledge. We believe that data discovery and experimentation are important, but that the path from discovery to hardened production should be short and should not require a shift in technology. We also believe that for a data lake to survive the test of time, it must be manageable. Resources must be easy to find and be well documented. Data needs to be secured and its flow tracked in order to uphold any covenants or regulations associated with it. These aspects are known as curation and governance. Enterprise data lake technology is a technology that supports the value extraction process from ingestion to end user delivery in a way that's secure, scalable, and manageable. A data lake will continuously acquire data from many external sources and ingest it. Data is usually stored in simple flat file-like formats such as basic disk files or name addressable forms such as Amazon's S3 or Azure blobs. These are efficient forms for the type of processing done within a data lake. Data lakes typically begin with a few data sources and some ideas for enhancement, and these expand dramatically over time. Once the data is ingested, the process of enriching the data begins. This is an evolving, iterative process of refining the data to extract as much useful knowledge as possible. No matter how valuable that accumulated knowledge is, it's only useful if it can be made available to the various people that need it in a timely and efficient manner. The data delivery process ensures the data is made reliably available to the appropriate users. Finally, it's important to have a process for curation, organizing, visualizing, and governing the data lake. There's a term for an uncurated data lake. It's known as a data swamp, and like its namesake, becomes an unpleasant and dangerous place to store your data and produces very little value. It's useful to contrast the database-centric approach with a data lake approach for dealing with complex data. In a typical database-centric approach, the needs of the user is assessed and a schema is defined that meets those users' needs. Then programs or scripts are written to take the various data sources and perform all of the transformations to merge and transform these sources into the final schema that all of the anticipated applications will use. If a new data source, application, or feature is needed, then the schema needs to be redesigned and agreed upon. Programs that load the database need to be rewritten, and all of the applications need to be reassessed for breakage or enhancements. This creates a tremendous barrier to change, slows down the value realization, and costs dearly in the development resources. The final schema is the only visible portion of the system. All of the transformation logic is hidden in the programs that populated it. Any aspects of the raw data that were not considered useful to the original application are not available to users until the schema is redefined. We contrast that to a data lake architecture. In data lake, all of the various stages of refinement are available for use by developers, from raw data to final application data. This can be built upon at any time to create new analyses, new user perspectives, or new applications without involving other teams. The full enrichment path is visible, as well as the specific logic of each transformation. Let's look at some of the benefits of data lake technology. As we discussed, the raw and intermediate results, as well as the final application data, are available for further value discovery and creation. This is necessary for a continuous value delivery process. New data sources, perspectives, and applications can be easily added to rapidly create value for the organization. Data lakes scale easily to any capacity. The use of flat files allows for maximum efficiency and parallelization. Forklift upgrades are not needed to scale capacity. It can be incrementally upgraded by adding component instances. Data lakes provide visibility into the entire data refinement and delivery process. This allows knowledge to be built up layer by layer with a natural cascade of value. Development teams can also scale efficiently without forced dependencies among teams or single points of contention. It's well documented that inter-team dependencies are the most common causes of project delays and cost overruns. I'll discuss later in my deep dive session how these dependencies can be nearly eliminated using data lake technology. In order to really understand the benefits and potential of data lake technology, we first need to take a swim in a data lake. Data exists in many forms: numbers, text, image, and video. The data available from public and private sources is increasing exponentially. New types and sources of data are becoming available continuously. This creates myriad new opportunities to harness that data and capture its value. I expect that these opportunities will continue to grow dramatically as more and more new sources and types of data develop. A data lake typically contains a large, complex set of data coming from multiple sources. We want to refine that data so that we can produce value in the form of structured information, insights, and in some cases, notifications, recommendations, or direct actions. None of us are smart enough to look at such a body of data and know where all of the value is hidden. We typically start with some surface level synergies, put those into production, and with those as a basis, we can see opportunities at the next level. This refinement process can continue indefinitely, and in many cases, new sources and opportunities will arise faster than we can utilize the value at hand. While we may never extract every nugget within our data, the process of discovery, extraction, continuous refinement, and productization will result in greater and greater value as time goes on. So the primary purpose of a data lake is what we call data enrichment. It's simply the process of producing value from digital data. We've talked about data. Let's talk a little bit about value. We tend to think of data as a commodity that can be developed, monetized, and sold. I'll keep using the dollar sign as a convenient symbol for value, but there are many forms of value that can be derived from data that are beyond monetization. Data has been used to find missing children, catch criminals, identify new materials and pharmaceuticals, understand the universe we live in, and save countless lives. It's hard to put a price on that. So how do we perform the alchemy of data enrichment? It's a complex, iterative process involving many different approaches and techniques. We can take a quick look at some of those. We start with accuracy. All public and most private data sources are fraught with errors, omissions, and irregularities. Simply repairing or removing these issues adds value. Businesses have been built on providing cleaned versions of publicly available data. Data will find surprisingly many ways to misbehave. Some data may respond perfectly well to certain types of analyses, while other types may expose subtle issues that must then be corrected. Basic statistical analysis provides insight into the nature of the data. Aggregations, averages, trends, ratios, and comparisons can all provide enhanced value. Metrics can be viewed as statistics with meaning attached. They're specific to the domain you're working within, and while some are standardized, adding insight often requires the creation of new metrics. Metrics are often used as a window into phenomena that are not directly measurable. The Consumer Price Index metric is an attempt to measure changes in the purchasing power of the dollar from the average consumer's perspective. The FICO score is an attempt to assess a customer's creditworthiness. Scores, ratings, indices, and indicators are all various types of metric. Coverage is the process of expanding the reach into more and more of a certain type of data. Data on one company is good. Data on a whole industry is better. Data from the state of Florida is useful. Data from multiple states or the whole country can be much, much more valuable. Breadth is expanding from the data you have to different types of data that are complementary. Increasing the scope of the data lake with synergistic data opens up whole new possibilities for enrichment. Sometimes these synergies are obvious, but other times can be surprising. Entity resolution can be a very challenging yet extremely rewarding enrichment activity. It is the process of identifying entities which the data describes. Without it, I may know the name of a business that owns a patent, but can't enumerate the patents that a business owns. That's because most relationships you'll find in public data are descriptive, and descriptions tend to be ambiguous. Various techniques can be employed to convert descriptions into defined entities. Relationship resolution is often intertwined with entity resolution. Which John Smith was an inventor on a patent owned by IBM? And what other patents did that John Smith develop? Qualitative analysis defines non-numeric attributes. They can be simple thresholds such as good, fair, or poor on a credit score, or maybe based on complex assessment or even machine learning classification. Rating a stock as buy, hold, or sell is a good example of a complex qualitative metric. Diagnostic inference detect anomalies such as fraudulent transactions, an error in a process, or an overloaded server. These inferences can be used to signal users to further analyze a situation, or in some cases, to perform an automated action such as locking an account. Finally, prediction can be used to understand the future expectations of a time series or to determine the value of an unobserved variable given a set of observed variables. Prediction typically involves machine learning technology. This is just one possible taxonomy of the data enrichment process. In fact, between finalizing my slides a week ago and today, I embarrassingly noticed two more important dimensions that I neglected to include. I bring that up now because they are relevant to some of the other talks you'll hear today. The first I call extraction. I would place it somewhat arbitrarily between statistical analysis and metrics development. It is the process of making unstructured information available for analysis. In David DeHilster's NLP++ presentation, he'll talk about extracting information from text. He'll describe the challenges of what on the surface may seem as a reasonable, straightforward parsing task, and describe his state-of-the-art platform plugin for handling such tasks. After the breakout sessions in my ML and machine learning advancements talk, I'll be discussing how to extract data from images or videos. The second one is visualization. This I would place between metrics development and coverage. Value is often added through improved visualizations. We'll be demonstrating that in the COVID-19 Data Lake breakout session and talking about it in several others. There's a lot more to data enrichment than meets the eye. It's an iterative process. Each breakthrough creates a cascade of other avenues to explore. I have yet to come to the point where I can't find any more value to add in any data realm I've explored. In my Data Lake deep dive session during the breakouts, we'll explore data enrichment in more detail and talk about how to get started with your own data lake. The practice of data enrichment is as much an art as a science. It requires a certain mindset and skill set and crosses many disciplines: data science, causality, statistics, machine learning, computer science, and software engineering. I call this role a data engineer, and I hope some of you who are maybe at the early stages of your career consider data enrichment or data engineering as a career path. I'm quite sure that it will be at the nexus of many advancements in human understanding to come. Let's take a deeper look at the requirements for an enterprise data lake. An enterprise data lake must be scalable, resilient, and secure. It must seamlessly allow for both data exploration and hardened production. It must provide for curation and governance and be able to integrate into existing systems and processes. HPCC offers the most fully functional and robust solution for building enterprise data lakes. It has been proven in a wide range of industries and operates some of the largest and most complex data lakes in the world. The time-tested solution that has sustained data lake through data lakes through tremendous evolution and expansion of both data and users. It is used in mission-critical applications with extremely tight service level requirements. HPCC Systems open source data lake solution can run on a basic laptop, or it can be scaled to thousands of servers and petabytes of data. As you saw, it can run on-premise or in the cloud. It's secure and auditable, and used to manage some of the most sensitive information for large and diverse user bases. In my data lake deep dive, we'll look at the various components and the advantages provided by HPCC. If I've managed to pique your interest, there's an entire track related to data lake technology and the practice of data enrichment. At 10 o'clock, I'll continue this discussion at a deeper level of detail with a data lake deep dive. At 11, we'll look at the experience of building a COVID-19 data lake to enhance the value of publicly available COVID data. And at 1 o'clock, our colleagues from North Carolina State University will discuss their experiences building a data lake for agricultural data. I hope you can take the time to attend one or more of these talks. I thank you for your time and attention, and I think we still have some time for questions.
Thank you very much, Roger. This was very good. I really enjoyed your presentation. Well, I enjoyed both, of course. But I will ask you maybe a question. We don't have much time now because you need to move to the next session, and you're fully booked today on sessions. But I have a couple of questions of my own. I didn't see any questions posted for this particular talk on the chat yet. And for those that are in the audience, in case you haven't explored the interface match, there is a queue at the bottom of your screen right there. And that letter Q is where you can ask questions. There is a chat there, and there's been quite an active chat with people answering and asking questions. So if you haven't and you have a question, please do not hesitate to click on that queue and enter your question, or even read some of the feedback that others have provided. So Roger, I have a couple of questions of my own. I'll ask you one of these. So you are explaining that we can and we should build a data lake using HPCC so we can aggregate data and also curate the data. One of the things that is quite important is always to be able to track and register in some way the source of the data provenance, because of course, in many cases you need to explain where the data came from, where that particular piece of information was obtained. So how do you explain that we should do this management of data provenance, particularly in HPCC-based data lakes?
Yes, I'll be talking in a deep dive session about a new component that's just being released in beta, which is called Tombolo, and that's the HPCC curation and governance system, and that will provide facilities for tracking the provenance of data as well as any covenants associated with that data.
So what time is that talk, Roger?
That talk is in 3 minutes, I believe.
Oh, then I let you go. Then I'll move on to the questions from Richard. That's great. And people, if you are interested in knowing about data provenance and data version and tracking, you should probably start moving on to the next talk. For those that like to get some of the questions and answers from Richard, please stay put. We are going to go through those next. Roger, thank you very much. And we'll go to Richard then. Richard?
Thank you.
So Richard, we have a few questions there from the audience, so I'm gonna go those first. The first one is from Jason, LAA. He's asking about a way to do some estimation of the cost of a particular work unit. You mentioned that we can scale now and run as much as we want, and there is no limit. The sky is the limit in the cloud. That sounds like a slogan. So how do the ASL developer know how much it's gonna cost to run a job? Arjuna replied that there is a work unit analyzer coming soon that will do some of this. And he also reminded the audience that there is a talk about HAT, the HPCC analytics tool, at 1 p.m. by Apar that will potentially cover some of this. But tell us, Richard, how do we do this? How do we know how much it's going to cost?
Well, the work unit analyzer will certainly help after the event of working out, why it cost what it did and how you can make it cost less next time. In terms of predicting in advance, you can indicate in the cloud, you can actually indicate on a per work unit basis how many nodes you want, how big the Thor is you want to run on. So you can, after a while, you'll soon learn that a 400-way Thor is going to cost you this amount for the compute nodes, at least. Data costs a bit harder to predict because if you're being charged per access without knowing in advance what the what data you're going to access, it's going to be hard to predict. This is one of the reasons why we said we need to try and put a guillotine in there so that if you think this is going to be a job that is going to cost $20 and it's worth $20 of your money to run it, you might want to say, well, if it ends up costing more than $20, kill it, rather than waiting till it's cost you $2,000 before discovering that actually it wasn't the job you wanted.
That is a very good idea. I like that. So having some sort of thresholds or limits,
yeah,
and define it. Yeah. And if you kill it, the idea would be that you still can have some of the work that has been done already recorded. So if it managed to execute a subgraph, maybe that's still there, and you can see how you do the rest.
Well, if there were persists in there, for example, those would still be around. I mean, quite often the reason why you'll kill it is because you realized there was a mistake in the job, for example, that it should only have taken 5 minutes, but you made a typo on it, and therefore it's going to run a bit longer. In such cases, you don't really want to preserve the information. But.
Good point. There is another question from Ola Osunkoya. So Ola was asking, you said, well, if you run on data centers, there is no issue. You can continue to run data centers. We will have that capability there, and we will continue to evolve and make it better. But Ola is asking, with our general push in LexisNexis resolutions towards zero trust, and the world is pushing to zero trust anyway, how feasible is it to continue to support this data center version of HPCC, or will we move some of the new developments that we are doing for the cloud also to the data center version, so you can still get those benefits?
Well, we would very much like in the future there to be a single version which would be targeting Kubernetes, and whether that Kubernetes is in the data center or the cloud, we don't care. Whether the Zero Trust initiative will accelerate that process or not, I suspect is a question that you're better placed to answer than I am.
Very good. Good point. Appreciate.
So what's the answer, Flavio?
I don't know. I don't know. I wasn't prepared for that question, Richard. Okay, very good. We are 1 minute, well, now 2 minutes out over. So let's move on to the next session's audience. We will respond to any other questions that might appear in the chat window through email or in some other way. So we'll get back to you with the answers if you post a question in the chat window after time. Thank you very much. Thank you, Richard, and thank you, Roger, even though he already moved on. This was a great session, and we look forward to seeing the audience in the breakouts, poster sessions, exhibit hall, and certainly throughout the plenary sessions at the end. And do not forget to vote on the posters and look at those digital badges if you get one. Thank you.